Hi, so thank you to the organizer. I'm trying to share. I think now it's okay.
Right.
Great. So as the organizer said, I will talk about engineered Swift equilibration, or ESE, of brownian particles and the consequences of hydrodynamic coupling. First, a few words of introduction. So I'm Dago, a PhD student in second year at the Laboratoire de Physique de l'ENS de Lyon, and I thank all my co-workers on this work. So you can see their names here. So to present you how I will explain things here, first I will present you ESE protocols. Then I will share you experimental results that confirms the efficiency of these ESE protocols to drive simple systems. Then I will question the stability against external perturbation of these protocols, and in particular, the robustness to coupling interaction. And this question of robustness will lead to the extension of the scope of ESE protocols to more complex systems. And in particular, I will finish by presenting ESE protocols designed for coupled systems. So first, let me present what is ESE protocols. So I introduce the system we work on. It is a single particle trapped in an harmonic potential by optical tweezers. So here you can see one of the particles we are working with, and the particle has a brownian motion, and it's trapped by the laser here. So as I said, the optical tweezers create an harmonic potential of stiffness K. So we can write it this way. It's just a simple harmonic potential. The particle we are working with are silica beads of radius 1 micrometers, and they are evolving in water at temperature T. And I will write in the following the position relatively to the trapping position X of T, to the trapping center, and the variance depending on time too. So now the question is, why use ESE protocols? The point of ESE protocol is to reduce the transient state of system and make them relax faster to the equilibrium state after change of a control parameter by controlling the profile of the potential between its initial and final values. This shortcut process is designed to speed up equilibration process. For example, let's imagine I want to start in this state of equilibrium with the potential here of initial stiffness Ki. The position distribution of the particle will be Gaussian, predicted by Boltzmann, and the variance should respect the Boltzmann equilibrium. And I want to go from this state of equilibrium to another state. I want to close up the well and change the stiffness into a new value, Kf. And this final equilibrium is characterized by the Gaussian distribution and the variance here given by the Boltzmann equilibrium. And there is two ways to do that. We can suddenly change the stiffness from Ki to Kf, and doing so, the particle will relax naturally in its natural relaxation time that depends on the dissipation and the potential strength. And it will last around 30 milliseconds in our system. This is the natural relaxation time. But it is also possible to pilot the system to its equilibrium several orders of magnitude faster than the natural relaxation time by imposing a specific form of the potential evolution, which is the ESE protocol. So here, this evolution of stiffness K of T enables us to reach the same state 100 times faster than the natural relaxation time. So now the next question is, how can I build this profile of stiffness that enables me to shortcut the equilibration process? So this can be done using theoretical physics tools and by retrocomputing from the evolution equations of the system. Here I'm working with an overdamped system, my particle in water, so I have to introduce the friction coefficient of water, and I can describe the movement of the particle by the Fokker-Planck equation here that introduce the probability distribution, rho of x and t, the probability of the particle to be in x at time t. And this Fokker-Planck equation depends on the stiffness profile k of t. And then the second equation I will need is this one that describes the evolution of the probability distribution. There's actually one strong property of ESE protocol is that the probability distribution will remain Gaussian all the time during the process, not only at the Boltzmann equilibrium. So we can write that at all time, the probability distribution is Gaussian and write this way, introducing the parameter I called alpha of t. This is the inverse of the variance, actually. So back to the construction of ESE protocol, the strategy consists in choosing a form of alpha that will satisfy the Boltzmann expression at t equals 0 and t equal to the final time tf, and then coming back and deduce the stiffness profile from the Fokker-Planck equation that connect the two quantities. For example, I will present you the basic ESE that drives single particle. In this example, I choose the simplest form of alpha that satisfies the steady state here and here of the Boltzmann equilibrium I want. And these steady states are obtained at s equal to 1. I introduce a new notation. S is just the time divided by the final time of the protocol. And the small k are the stiffness divided by the initial stiffness. So I choose this simplest form of alpha that satisfies all the requirements on the boundary conditions, and I deduce from the Fokker-Planck equation the stiffness, which is the red curve. So you can see if I want to compress the well to go from a wide well to a more narrow one, I have to compress a little bit more and then relax again. This is the overshoot you can see here before coming back to the final value desired by the experimentator. Just to confirm and to show you the simulation, if I solve the Fokker-Planck equation with this kind of profile in red, I obtain the variance evolution you have there with the particle in the steady state at the initial stiffness going to another steady state in the desired time. You can see that because the well is closing up, the variance decreases and reach its new equilibrium state. Now the question is, does it work experimentally? And some researchers at the Laboratoire de Physique of the ENS de Lyon developed an experimental demonstration of this basic ESE. They compared two methods to change the stiffness of the trap from the initial value here, 0.5 piconewton by micrometers, to Kf, which is the final stiffness. It's the doubled value, 1 piconewton by micrometers. To do so, on the one hand, they applied the red curve here, which is just a step function. And on the other hand, they apply, you can recognize here with the overshoot, the basic ESE protocols. And the results are on the right. You can see that with the step function, the sudden change in stiffness, the system will relax slowly in the natural relaxation time of the system, 30 milliseconds. But with the ESE protocol, you can see that the process is really speed up because it reached its new equilibrium at the desired time TF, just as we wanted. So here they choose TF equal to 0.5 milliseconds, but you can choose whatever final time you want. If you want to decrease the final time, as a consequence, the overshoot here of the protocol will increase. So you will have to compress a lot more before releasing the well. And as a matter of fact, the work required to apply this protocol grows as 1/TF. So there is a price to pay to shortcut like that the equilibration process. And now the question in the third part of the presentation will be, is this ESE protocol, the basic ESE protocol, robust to coupling interaction? And in particular, can it be used for more complex systems. So to do that, we will now tackle the case of two particles hydrodynamically coupled by trapped in different potentials, but because they are near one to another in the water, they are hydrodynamically coupled. And we want to understand to what extent the equilibration dynamics imposed by the basic ESE is modified by the hydrodynamic interaction with another particle at a distance d. Now the system is the following: two particles that I said at a distance d, and I will try to extend the ASE protocol we had before to this coupled system. To do so, I will drive the two stiffnesses by the profile I showed you before, and I will call that the symmetric ESE. Again, some new notations on the dimensionless variances. I will just call it sigma here because it's symmetric. We are applying the same protocols on both traps, so the variance of the first particle is the same as the variance of the second one and can be called sigma. So now the question is, experimentally, how much deviation from the free case we obtain with this symmetric protocol? Here I applied the profile here. So first, a step decompression to bring back the system to the initial potential, the initial stiffness, and then a compression using the ESE protocol, as you saw before, with the overshoots, and then the end of the protocol here in the final value of the process. And the experimental results we obtained is here on the right. In black, it is the curve corresponding to a high distance between the particles, so we can consider there is no coupling in this case. And in purple, the distance between the particle is 0.7 micrometers, so they are strongly coupled. You can see that first, the natural relaxation seems to be affected by the coupling, because here the purple line seems to be slower, but the natural relaxation lasts around 30 milliseconds as expected. Then coming to the ESE protocol, you can see that the coupling induces a rebound here before reaching the final value. So instead of reaching the new equilibrium precisely at TF, we see here in purple the rebound. So to put it in a nutshell, this result highlights that even though the protocol is designed to be much faster than the coupling characteristics time, which is about 30 milliseconds, the coupling perturbation impacts the response to the basic ESE and prevents the particle to reach equilibrium in the expected time. So these are the experimental results. But the question is, does theoretical analysis predict this deviation from the free case? So to do so, I will present you here the model we selected to modelize our coupled system. So now we have coupled Langevin equations to describe the two brownian particles, and they are coupled by this tensor here, the Auchin tensor. And in some approximation, we can write that the coupling intensity, the coupling parameter epsilon, can be written this way. So here, if the distance between the particle is really high, the coupling constant will be equal to 0, and the tensor will be diagonal, and there is no coupling anymore. So we use this model and solve the equation, the two-dimensional Fokker-Planck equations, thanks to this model, to predict the behavior of the system in response to the symmetric ESE. And we obtain here this simulation, this computation. So this is the response to the same profile I showed you before for the experiment. In black, there is no coupling, and in blue, the coupling is very strong because the distance here is very, very low, 0.3 micrometers. So you can see that indeed the natural relaxation is also affected by the coupling, and it's slowed down. But what interested us is here the response to the symmetric ESE protocol. When there is no coupling, the shortcut is perfect. But when there is a strong coupling, you can see here again the rebound and then the natural relaxation before reaching the new steady state. To confirm that the model prediction and the experimental curves match, I superimpose here in dashed line the theoretical curves obtained using the same ESE parameters as the experiments and some external parameters such as the temperature, the viscosity, etc. from calibration. And we can see that the theory is very consistent with the experiment. The curves are very close. And this is really a nice conclusion for us because our model really fits the experiment. Now I will draw some conclusions on the consequences of coupling perturbation on ESE protocol. First, our sensitive experimental setup enables us to observe experimentally the tiny effects of hydrodynamic coupling, which is 10% rebound deviation from the zero coupling case. Nevertheless, the symmetric ESE is rather robust. As for moderate coupling, the rebound is modest compared to the natural relaxation amplitude evolution. And then, as I said, the theoretical model fits with experimental results. So it can be used to be at the basis of the construction of new ESE protocols adapted to the coupled systems. So now this is my last part. We will try to build protocol that drive coupled system without any compromise on the shortcut efficiency. So for the last part, first, I will draw some requirements and some simplification in order to find these ESE protocols for coupled system. As I said, we want to drive the first particle of the two coupled ones from the initial state to the final one in the desired time. And we want this driving to be robust to coupling interaction. And I add another constraint. I would like this to not depend on the coupling intensity epsilon, which means I would like to apply the same protocol, whatever the distance between the particle. And to do so, to have a protocol independent on the coupling intensity, it requires the particle independence at all time, not only at equilibrium. The ESE protocol that satisfies all these constraints I call it the coupled ESE. So doing the same as we did before, retrocomputing on the two-dimensional, this time Fokker-Planck equation, we obtained the stiffness profile of the coupled ESE. In red, you have the profile to apply on the first well, and in blue, the profile to apply on the second trap. The expression of K1 here is the same as the single particle case, but the second potential has to be driven with a different stiffness profile. The price to pay to drive correctly the particle 1 from the initial state to the desired final one is to impose a nearly opposite profile on the second potential. And there is a price is that the final value of this evolution of the second trap cannot be chosen. It depends on the ESE parameters. So now we obtain this coupled S profile. The question is the same. Does it work experimentally? So we conduct the experiments in order to compare the two. First, we conduct the same experiment as before with the symmetric ESE, and we obtain the rebound we had before, naturally. Again, in dashed line, the theory is very consistent with the experiment. And now, if we apply the coupled S with the two traps driven independently, as I showed you on the former slide, we obtain the black curve here. This is the experimental results. And in dashed line, the theoretical prediction. You can see that the coupled S totally suppressed the rebound we observed on the basic ESE protocols. So as a conclusion, thanks to this process, we achieve the same efficiency of shortcuts we had on single particle, but now for coupled ones. Now I think it's time to conclude. Let me summarize what I explained during this presentation. First, I talk about the basic ESE that is built to drive single particles, and I showed that in experiment it speeds up perfectly the equilibration process. But the question was, can we extend this protocol to more complex systems and to coupled ones? It was the symmetric ESE when I tried to apply it to both particles. And this proved a relative robustness because it's only 10% deviation. But if we want to do better, we have to construct a new family of ESE protocols robust to coupling interaction. To do so, we use the model of hydrodynamic coupling, which was consistent with the results we had. And we built a new ESE solutions immune to the coupling interaction. This was the coupled ESE. And we show that experimentally, it speeds up perfectly the equilibration process. And it's epsilon independent, so we can work for any distances between the particle. And it has one particularity, that it enforces independence between the particle by suppressing the cross correlation. Of course, there is other solution to find to try to extend these ESE protocols to complex systems. So this is the end of my presentation. Thank you very much for your attention. Thank you again for the organizer and the organization. And if you have any questions, please feel free.